Welcome today to our presentation about multimodal 3D object detection. Hello, everyone. I am Ziying Song, a second-year PhD student from Beijing Jiaotong University in China. I would like to express my sincere gratitude to my esteemed collaborators, Wei, Bai, Dr. Yang, and Professor Jia, for valuable contributions to this research endeavor. Now, I am delighted to present our work on multimodal 3D object detection for autonomous driving. LiDAR and cameras are complementary sensors for 3D object detection in autonomous driving scenarios. However, it poses a significant challenge to effectively exploit the complex interactions between point cloud data and images. The critical factor in this challenge lies in achieving accurate feature alignment across heterogeneous sensor modalities. Currently, many existing methods attempt feature alignment solely through projection calibration. Unfortunately, these approaches often neglect the issue of coordinate conversion accuracy errors between sensors, resulting in suboptimal performance. In the real-world scenario, accuracy errors arise due to disparities between LiDAR and camera sensors. Specifically, in the fusion of features over long distances, the misalignment of small objects leads to a decrease in detection performance. As illustrated in figure, the data stream is firstly fixed into a data frame with a given timestamp when passed into the on-device computer. Then one needs to perform the coordinate transform via the camera-to-world and LiDAR-to-world matrix that is obtained by the calibration process. However, this leads to potential ill-synchronization issues, spatial misalignment due to the external reasons of calibration matrix and temporal misalignment for both LiDAR and camera data due to internal system reasons. In this paper, we present GraphAlign, a more accurate feature alignment strategy for 3D object detection by graph matching. We adopt the LiDAR-only detector voxel RCNN and center point as the baseline. Fig shows the network architecture. Specifically, we fuse image features from a semantic segmentation encoder in the image branch point cloud, features from a 3D sparse CNN in the LiDAR branch. To save computation, we construct the nearest neighbor relationship by calculating Euclidean distance within the subspaces that are divided into the point cloud features. Through the projection calibration between the image and point cloud, we project the nearest neighbors of cloud features onto the image features. Then by matching the nearest neighbors with a single point cloud to multiple images, we search for a more appropriate feature alignment. In addition, we provide a self-attention module to enhance the weights of significant relations to fine-tune the feature alignment between heterogeneous modalities. GraphAlign comprises two key modules: graph feature alignment and self-attention feature alignment. The GFA module divides the point cloud space into subspaces and generates the k-nearest neighbor features for each point cloud. It then transforms the local neighborhood information of the point cloud into image neighborhood information via a projection calibration matrix, followed by one-to-many feature fusion between a single point cloud feature and k-neighbor image features. After obtaining the fused features in the GFA module as mentioned above, the aggregation relationship between these features and their k-neighbors was found to be underestimated. To overcome this limitation, we introduced the SAFA module as a complementary component to the GFA module. It employs self-attention mechanism to amplify the important significant fusion features, as illustrated in figure. We present the details of each dataset and the experimental setup of GraphAlign, and evaluate the performance of 3D object detection on Kitty and Nussens datasets. Since Kitty and Nussens are distinct datasets with varying evaluation metrics and characteristics, we provide a detailed description of the GraphAlign settings for each dataset in the following section. We validate our GraphAlign on the Kitty dataset using voxel RCNN as the baseline. We validate our GraphAlign on the Nussens dataset using centerpoint as the baseline. Experiments are conducted using the Kitty and Nussens benchmarks, demonstrating that GraphAlign can boost point cloud detection accuracy, especially for long-range objection, as shown in tables. We compare GraphAlign with state-of-the-art methods in 3D and BEVAPs on KITTI test dataset. We observe that our GraphAlign achieves state-of-the-art performance. We also conducted experiments on the much larger Nussens dataset using the state-of-the-art 3D detector center point to further validate the effectiveness of our GraphAlign. Our GraphAlign exhibits excellent performance in small object detection, particularly for categories that are characterized by a higher proportion of small objects at long distances, following more accurate feature alignment, building upon existing projection-based and attention-based feature alignment strategies. We hope that our work can provide a new perspective for multimodal feature fusion in autonomous driving. Thanks.